In this video, we'll talk about what antiderivatives are. So we say that a function capital F of x is an antiderivative of a lowercase f of x if the derivative of capital F of x equals the function lowercase f of x. So let's give an example. So for example, if capital F of x was the function x cubed, its derivative, so the derivative of this, well, we know what that would be. I'm going to call it lowercase f of x. But the derivative of x to the third is this just equals 3x squared using the power rule. So that means, according to this statement, that capital F of x, x to the third, this is an antiderivative of the function 3x squared. So going in this direction, this would be an antiderivative. Okay, so that said, we are ready to give a more formal definition. So we say that a function capital F of x is an antiderivative of lowercase f of x on an open interval I if, and what I need is I need the derivative of capital F of x to be equal to lowercase f of x for all values of x in that interval I. Okay, so there are a couple of remarks I want to make about this. The first is this antiderivative of capital F. This is not unique, which means there can be more than one. So in the example we just did, e.g. if our function lowercase f of x was 3x squared, let's write two possibilities for antiderivatives, then two possibilities for antiderivatives, capital F of x, are, well, one value we gave was x to the third. Another one would be something like x to the third plus 5, because if I take the derivative of this, if I take the derivative of x to the third plus 5, it's still going to be 3x squared. So I'm gonna make a note of that. So this works because d dx of 5, the derivative of 5 is just 0, because it's a constant. In fact, if I were to write any constant here after the x to the third, it would be a valid antiderivative. So there are actually infinitely many possibilities. All right, so a more general antiderivative of this function, lowercase f of x equals 3x squared, is, I could write capital F of x equals x to the third plus c. I'm going to write capital C here, where capital C is a constant. So a constant just means it is some fixed real number, like maybe x to the third plus 5, maybe x to the third minus 12.18. So some fixed real number. All right, so why does this make sense graphically, that a function could have more than one antiderivative? Because when we do derivatives, there's just one. Well, let's look at this example. So graphically, so I'm going to call the first antiderivative we wrote f1. So I'm going to say that's x cubed, and I'm going to call the second antiderivative we had f2. So that'll be x to the third plus 5, and I want to look at their graphs, and I want to compare that to the graph of the derivative function, lowercase f of x, which remember was 3x squared. So I'm going to make three sets of axes here. So I'll make an axis for the x cubed graph. Let's make an axis for the x cubed plus 5 graph, and then an axis for the derivative graph, for the graph of 3x squared. So x cubed, we know what this graph looks like. It sort of snakes upwards like this, gets flat here momentarily at the origin, and then it continues snaking on upwards. If I add 5 to that function, that's going to shift the whole graph up 5 units. So this point that used to be at the origin is now going to be 5 units up, and our graph will look something like, it'll look something like this. It sort of snakes downwards, and it Let me draw that a little better, and it snakes upwards this way. Okay, so after it shifts up 5 units, now this point is at 0, 5. And if we look at the graph of 3x squared, well, this is an upward-facing parabola. And the vertex is at the origin. So it looks something like this. So the key fact I want to recall is that the derivative is the slope of a tangent line. So I'm going to label some x coordinate here. I'm going to call this A. So let me put the same x coordinate here on this graph. And at those x coordinates, I'm going to draw a tangent line. So on this x cubed graph, that tangent line would look something like this. And then on the graph of x cubed plus 5, that tangent line would look something like this. But I noticed that those lines have the same slope. At least if I drew this graph well enough, they would have the same slope. Okay, and on the 3x squared graph, if I draw that same x coordinate, notice that the output is positive, and that matches with the fact that the slopes of these tangent lines were positive. They were at least a little positive. Okay, let's confirm this with a different x coordinate. What about if I did something over here on this side? Let me call this one B. Let me go the same distance over here, B. So I notice that if I draw that tangent line on the x cubed graph, this one's very positive. And on the x cubed plus 5 graph, well, let me draw that one better. I have this, and it's something like this. It's the exact same slope. And that makes sense because all that happened was just the graph got shifted up, but that's not going to affect how steep this tangent line is. And on the derivative graph, if I label where B is, that output is way higher. And that matches with what we're seeing in the antiderivative graphs because these slopes are very positive. These are very steep. All right, so the slopes of f1 and f2 are equal at corresponding points on the graph. So at both of the points where the x-coordinates A, the slopes of the tangent line were the same. And both of the x-coordinates when they were B, the slopes of those tangent lines are the same. And so this makes sense. It makes sense that they would both have the same derivative, or aka that they are both antiderivatives of lowercase f of x. This makes sense why they are both antiderivatives of lowercase f of x. Okay, so if we go back to this technical definition that we had of an antiderivative, notice that it mentioned something about, this open interval. So I want to ask the question now, well, why is that open interval part in this definition necessary? So why is that open interval necessary? And it has to do with the fact that if we have a discontinuity somewhere in our interval, discontinuities can yield multiple constants in that general antiderivative formula. So let's take a look at an example. So for example, let's say lowercase f of x is 1 over x squared. And 1 over x squared, I want to be able to take the antiderivative of this. But remember, 1 over x squared is x to the negative 2. So some possible antiderivatives of this, are, so I'm going to write 3 of them. So one, I'm going to call it capital F of x for antiderivative. One possible antiderivative of this would be negative x to the negative 1. And I could check it. If I were to do the derivative of this with power rule, I would get x to the negative 2. Okay, and I could rewrite this. This is negative 1 over x. But of course, I could just take that function and add some constant to it and get another antiderivative. So if I did capital F of x equals negative 1 over x plus some constant like 3, this should also be an antiderivative. Because if I take the derivative of this, I will still get 1 over x squared, because the derivative of 3 is just 0. But I can also get the same thing if I took a piecewise function. So what if I had something like negative 1 over x? If x is less than 0, but I had something like negative 1 over x plus 3 if x was greater than 0. So this third function here, it still has the same domain as 1 and 2. The domain is still all real numbers except for 0, but the derivative is going to be lowercase f of x, because the derivative of both of these pieces is 1 over x squared. So, but the most general, if I use this idea now to write the most general antiderivative, the most general antiderivative of lowercase f of x equals 1 over x squared is, it's going to be a piecewise function. I would have capital F of x equals, and I could have a piece like, so I'm going to have one piece where x is less than 0. This is going to be on one side of the discontinuity. This is going to be discontinuous where x is 0. And there's going to be another piece when x is greater than 0. That's on the other side of the discontinuity. So I could have negative 1 over x plus one constant, like I'll call it c1. And then I could have negative 1 over x plus some other constant. I'll do this, call this plus c2. This would be the most general antiderivative. So we could verify this graphically, that this makes sense. If I were to look at the original function, lowercase f of x, which is 1 over x squared. So that graph is going to have one piece over here. 1 over x squared has one piece over here, and it's got a symmetric piece on the other side of the y-axis. Turns out this is an even function. This is symmetric about the y-axis. Okay, and if I look at this function capital F of x and what that looks like. So capital F of x. So I'm going to have this piecewise function. Okay, so I'm just changing the color on how I wrote those pieces so I can color in my function in the same way, just so it stands out more. But to graph this, remember that the graph of, remember that the graph of something like y equals 1 over x, that graph we know, it's got one piece over here, one piece over here, and if you have a negative 1 over x, that's going to reflect this whole thing across the x-axis. So this piece that's up here will now be flipped down here, and the piece that's down here will get flipped up across the x-axis, and it'll look like that. Okay, so our graph, when x is less than 0, that's the left-hand side of this negative 1 over x graph, and that's going to get shifted up by c1. So let's just say for the purpose of this graph that maybe c1 is like 0. So maybe let's just say that this is y equals c1. It's just a horizontal line, kind of like I had drawn up here in my example 3 up here. Okay, so if I did that, that graph wouldn't get shifted at all. We'd kind of draw it as it is. And we'd have something like this. Okay, and then for this other piece, whoops, let me actually put it in purple. All right, so I put it in purple just so it matches the color in this piecewise function. So now this other piece, when x is greater than 0, that's going to look like the right-hand side of this hyperbola, this negative 1 over x function. Okay, and it's going to get shifted by c2, by some other constant. So maybe just for the purposes of my picture, maybe I'll say it's something like plus 3, some positive number. So that's going to also shift up that horizontal asymptote. And this is going to be y equals c2, whatever c2 happens to be. So if I draw in that part of the graph, that part of the graph will look something like this. So one of the things that I notice, if I check tangent lines and see if they make sense, is in the graph of f of x. Because of this symmetry about the y-axis, if I take 2 points that are sort of like the same distance away from the x-axis, their y values are the same. So I expect that when I go to the graph of capital F of x, this antiderivative graph, that when I draw the tangent lines at those x values, that they should have the same slope, because I see the same output in this derivative graph. Okay, so if I were to do that, so at this x value and at this x value, so if I draw those points and I draw tangent lines at those points, so this tangent line looks like something like this. This tangent line looks something like this. Okay, not perfect, but you know, it seems plausible that they have the same slope. And that makes sense based off of what we're seeing in the graph because this graph is the graph of the derivative of capital F of x, and we're seeing the same outputs at those x values. All right, so next I want to make some notes about what we're seeing here when we have these discontinuities. So the first note is that in order for the most general antiderivative to have one constant, c, my function lowercase f of x must be continuous on whatever interval capital I we're talking about, because a discontinuity means the antiderivative may have a different vertical shift on either side of the discontinuity, as we saw in this example above. The second note, we will assume that the interval I is such that the original function lowercase f of x is continuous on it, which basically means we won't worry about discontinuities, so we'll just have one constant, unless a problem specifically says otherwise, unless it tells us, oh, worry about that discontinuity, and so then we have to put multiple constants, but we'd only do that if a problem specifically tells us to. Otherwise, we will just write one constant. All right, so I want to end this video by talking about some notation. So recall that to take the derivative of a function lowercase f of x, the way we write it is we can write d dx of f of x. And that means the derivative with respect to the variable x in this function f of x. But to take an antiderivative of lowercase f of x, we will write, well, we'll call it capital F of x. But the way I say take the antiderivative, because taking the derivative is d dx, the way I say take the antiderivative is we will write this symbol, which is an integral, and then I write f of x, and then after that I write dx. And the dx is a notational thing, kind of like d dx, which is telling me the variable is x. But this integral, this is called, it's what's called an indefinite integral. So in the next chapter, we will see what definite integrals are. All right, so for example, we just saw that the general antiderivative of 3x squared dx, we would say, we saw that this general antiderivative was x to the third plus c, plus some constant c. So in terms of our goals for this section, we finished our first goal, discussing what antiderivatives are.